The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so welcome back, everybody. Happy to see you again. So today we are going to continue our exploration and to understand single harmonic oscillator. And this is actually the list of our goals. And we would like to learn how to translate physical situations into mathematics so that we can actually solve the physical problems we actually have and predict what is going to happen afterward. And we also sort of started to this course by solving really simple examples, single harmonic oscillators. And as a function of time, you will see that from next class, the next lecture, we are going to bring in more and more objects. And of course, more objects means more excitement also in terms of phenomena, but also more complication on the mathematics. So we'll see how things goes. And then after that, we are going to go to infinite number of oscillators and see what will happen. Of course, we will produce waves. That's very exciting. Then we'll do all kinds of different tricks to those waves. Okay. So what have we learned last time? So last time we went over an example, a simple harmonic oscillator. It's actually a rod fixed on the wall, and you can actually go back and forth. And we also introduced a model of the drag force or drag torque, and it's actually proportional to the velocity of the motion of the single particle. And the interesting thing we learned last time is that we have three completely different behaviors if we actually turn on the drag force. The first one is underdamped. The damping is actually very small. Then we have the solution in this form. It's oscillating. The amplitude is decaying exponentially. And as we increase and as we make the drag force larger and larger, it will pass a critical point, which actually give you a solution which you don't have oscillation anymore. The cosine disappeared. Finally, if you use, you actually put the whole system into water or introduce something really dramatic, very, very big drag force, then you have overdamped situation, and you see that the solution is actually a sum of two exponential functions. So this is actually the one equation which actually works for all the damped system we discussed up to now. And that is actually the map. Basically, if gamma goes to 0, gamma is actually control the size of the drag force. Then we got no damping. Then you have a pure, simple harmonic motion. And as we increase the gamma, then you can see that the behavior is changing as we increase the gamma. So you can see that we can use a quantity which is called Q. Q is actually defined as a ratio of omega 0, which is actually the natural frequency, angular frequency of the system. Okay? And gamma is actually a measure of how big the drag force is. If we make a ratio of these two quantities, then you will see that at Q equal to 0.5, it reaches a critical point, which actually the behavior of the whole system changed, and you can see that the oscillation completely disappeared. Okay, so that is actually what we have learned last time. So what are we going to do today? We have been really doing experiment really without our hands on, right? So basically we prepare the system, then we release it, then we don't touch it again and see how this system actually evolves as a function of time, right? So that's actually what we have been doing. So today, what we are going to do is to start to drive this system, okay, we can introduce some kind of driving force and see how this system will respond to this external force. Okay, so that is actually what we are going to do. And that will bring us to the situation of damped driven harmonic oscillator. Okay, so let's immediately get started. So we will use the example which we went through last time as a starting point. So the example from the last lecture is a rod which is fixed on the wall, and the length of this rod is L/2, and I define a counterclockwise direction to be positive, and I measure the position of the rod by this theta, which is the angle between the vertical direction and the pointing direction of the rod. Okay. And we have went through the math, and we got the equation of motion without external force, which is already shown on the blackboard. So now, as I mentioned in the beginning, I would like to add a driving force, or say a driving torque, tau drive. Okay, this is equal to d0 cosine omega d t. Okay, so I am adding a driving force with a driving torque. The amplitude of the torque is actually d0. Okay, and it's actually also a harmonic oscillating force or torque. And the frequency, the angular frequency of this torque is omega d. Okay, and that means our total torque tau of t will be equal to tau g t. This is actually coming from the gravitational force plus tau drag, which is to account for the drag force, and also this time we are adding in the tau drive. Okay, so I'm not going to go over all the calculation how to derive from the beginning to the end, but I will just continue from what we actually started last time. So if I have additional driving torque there, that means my equation of motion will be slightly modified. This time, my equation of motion will become theta double dot plus gamma theta dot plus omega 0 square theta, and that is equal to d0 divided by I. Okay, this is actually divided by I because in order to get acceleration, I need to divide my torque by a moment of inertia of this system, and cosine omega dt. This is actually the oscillating frequency of the driving torque. Okay, and just a reminder, gamma is defined to be equal to 3b over NL squared, and the omega 0 is actually defined to be square root of 3g over 2L. Okay, so as I mentioned in the beginning, this is actually giving you a sense of the size of the drag force, and the right-hand side, the omega 0 is actually the natural angular frequency. Okay, so of course we can actually simplify this by replacing this term, this constant, by a symbol. So the symbol I'm choosing is F0. Okay, and this is defined to be d0 divided by I. Okay, therefore I arrive my final equation of motion, theta double dot plus gamma theta dot plus omega 0 square theta, and that is equal to F0 cosine omega dt. Okay, so I hope this looks pretty straightforward to you. So this is our equation of motion. You can see from this slide. So we have three terms in addition to the theta double dot. The first one is actually related to drag force or drag torque. The second one is actually related to so-called spring force, right? So that is actually related to the spring constant, or because of the restoring force of the gravitational force. Okay. The third one is actually what we just added in, the driving force. Okay. So one question which I would like to ask you is, okay, so now I bring one more complication to this system. So now I'm driving this system with a different frequency, which is omega d. The question is, what will be the resulting oscillation frequency of this driven harmonic oscillator? What is going to happen? Well, this system actually follow the original damped oscillator frequency, omega, which is actually close to omega 0. Or will this system actually follow the driving force frequency? Finally, maybe this system chooses to do something in between. We don't know what is going to happen. Okay? So our job today is to solve this equation of motion and to see what we can learn from the mathematics. Then actually we can actually carefully check all those results to see if that agrees with the experimental result, which through those demos. Okay? So as usual, I have this equation of motion here. So one trick which I have been using is to go to a complex notation, right? Therefore, I can now rewrite this thing to be z double dot plus gamma z dot plus omega 0 square z, and that is equal to f0 exponential I omega dt. Okay, so basically I just go to the complex notation. And we would like to solve this equation. So in order to solve this equation, I make a test function. I guess z of t have this functional form. This is equal to a, some kind of amplitude, okay? Exponential I omega dt minus delta. Delta is actually some kind of angle, which is actually to account for the possible delay of the system. Okay, so if I start to drive, for example, this is a system which I'm interested. I start to drive this system. It may take some time for the system to react to your driving force, right? So that's actually accounted for by this delta constant, okay? And the amplitude is actually what we were wondering what would be the amplitude. Therefore, you have some kind of constant in front of the exponential function. And you can see that this exponential is actually having angular frequency of omega d, and that is actually designed to cancel this exponential I omega dt here in the drag force. Okay, so now we can actually calculate what z dot of t will be equal to I omega d z double dot t will be equal to minus omega d squared z. Okay, with those, we can now plug that back into this equation of motion and see what we can actually learn from there. Okay, so basically what I'm going to do is to insert all those things back into the equation of motion, and that is actually going to be like this. Basically, the first term, z double dot, you get a minus omega d squared out of it. The second term, gamma z dot, I have the z dot here. Basically, I will get plus I omega d gamma out of this the second term. the third term, I get omega 0 squared out of it. And that is actually multiplied by z. And this is equal to f0 exponential I omega dt. Okay? All right? And we also know from this expression, okay, z is equal to a exponential I omega dt minus delta. That's the test function. So this is actually equal to a exponential I omega dt minus delta. Okay? So now what I can do is that, I have some constant in the front multiplied by exponential I omega dt. And now I can actually cancel this exponential I omega dt with the right-hand side term. Very good. The whole system is actually, the whole equation is actually exponential free, right? Okay, and now I don't have any exponential function left. And the exponential I delta is actually just a constant. So it's actually, now this equation is actually independent of time. Okay? So what I'm getting is like this. Basically, if I multiply both sides by exponential I delta, then I get minus omega d squared plus I omega dt plus omega 0 squared a. And this is going to be equal to f exponential I delta, because I multiply both sides by exponential I delta. Okay? And this is equal to f cosine delta plus if sine delta. Just Euler's equation. Okay? Any questions so far? Okay, so look at what I have been doing. So I have this equation of motion. As usual, I go to complex notation. Then I guess z equal to a exponential I omega dt minus delta, because my friends from the math department already solved this, and I'm just following it. Okay. Then I can calculate all those terms, plug them in, and basically you will arrive this equation. Okay. This equation is a complex equation, right? So what does that mean? That means one equation is equal to two equations, right? Because you have the real part, you have the imaginary part, okay? Therefore, that's very nice because I have two unknown. The first one is a constant, and the second one is delta. Now I have two equations. I can solve what would be the functional form for a and the delta. And let me go immediately solve this equation. So if I take the real part from this equation, basically what I'm going to get is omega 0 squared, this is real, minus omega d squared, okay, this is also real, times a. A is actually some real number, okay. This is actually equal to f cosine f0. Sorry, I missed a 0 here, okay. So there are 0 I missed, okay. It should be f0, okay. f0 cosine delta, okay. And I can also collect all the terms, which is imaginary terms. Then I get only the second term from the left-hand side is with an I in front of it, right? Therefore, I get omega d gamma a, okay, from the left-hand side. And from the right-hand side, there's only one imaginary term. Therefore, I get this is equal to f0 sine delta. Okay, so now I have two equations. I have two unknowns. Therefore, I can easily solve a and the delta. Okay, so I call this equation number 1. I call this equation number 2. So now I can sum them in quadrature, the two equations in quadrature. And left-hand side will give you a square omega 0 square minus omega d square squared plus omega d square gamma square. That is actually coming from the second equation. Okay. That gives you the left-hand side. It's just a squared sum of the first and second equation. Okay. And the right-hand side will become f0 squared cosine squared delta plus sine squared delta. Okay? And this is actually equal to 1. Right? So that's actually the trick to get rid of delta. Okay? Then I can get what will be the resulting A. A is actually a function of omega d. Okay? Omega d is given, okay, to you. It's actually determined by you, right? How fast you want to oscillate this system, okay? And this is equal to f0 divided by square root of this whole thing, right? So this will give you omega 0 squared minus omega d squared squared plus omega d squared gamma squared. Okay? Then we can also calculate what will be the delta. The trick is to take a ratio between equation number 2 and the equation number 1. 2 divided by 1, basically you will get tangent delta, right? This is sine divided by cosine, right? F0 actually cancel, right? And this is equal to what? Equal to the ratio of these two terms, right? After you take the ratio, A drop out, right? Basically, what you get is gamma omega d divided by omega 0 squared minus omega d squared. Okay, so we have solved A and the delta through this exercise. Okay, so what does that mean? Originally, I assumed my solution to be A exponential I omega d t minus delta, right? Therefore, I would like to go back to the real world, which is actually theta, right? So basically, if I take the real part, I will get theta of t, which is actually the real part of z, okay? And that will give you A omega d cosine omega d t minus delta is also a function of omega d. Okay? So we have done this exercise, and you can see that the first thing which we see here is that there's no free parameter from this solution, right? A is decided by omega d. And delta is also decided by omega d, right? It's a lot of math, but actually we have overcome those. And then we have the solution. But it is actually clear to you that this cannot be the full story, right? Because you have a second order differential equation. You need to have two free parameters in the solution, okay? What is actually missing? Anybody can tell me what is missing? Very good. The homogeneous solution is missing. Okay, so that's actually why we actually have no free parameter here. Once the omega d is determined, once the f0 is given, then you have the functional form which decide what is actually theta. Okay? So what is actually the full solution? for full solution should be, as you said, a combination of homogeneous solution and the particular solution which we actually got here. So if I prepare the system to be in a situation of, for example, underdamped situation, okay? Then what I'm going to do is actually pretty simple. What I'm going to do is to just to copy the underdamped solution from last lecture and combine that with my particular solution, which I obtained here, okay? So let's actually see what this actually the full solution looks like. So I have A omega d cosine omega dt minus delta is omega d. It's a function of omega d. Okay, this is actually the so-called the steady state solution. Okay, and of course, as you mentioned, I need to also add the homogeneous solution. And basically, that is actually, according to what I wrote there, have a functional form of exponential a exponential minus gamma over 2t cosine omega t plus alpha. So I change a to b because I already have the a there, just to avoid confusion. Okay, then basically you get b exponential minus gamma over 2t cosine omega t plus alpha. Okay, basically there are two free parameters, b and alpha. Those two free parameters can be determined by initial conditions. Okay, so for example, initially I actually release the rod at some fixed angle of theta initial, and also the initial velocity is 0, then I can actually plug this solution in using those initial conditions to solve B and the alpha. Okay? Any questions so far? Yes? Yeah, I am assuming it's underdamped situation. Okay, so that's the assumption. So if the it depends on the size of gamma and the omega 0, right? Then you actually have actually 4 different kinds of solution, right? If gamma is equal to 0, then what you are going to plug in is the solution from no damping as your homogeneous solution, okay? And if you prepare this system underwater, damping is colossal, is huge, then you actually plug in the overdamped solution to be your homogeneous part of the solution. Okay? Any other questions? Very good question. Okay. So now maybe you got confused a bit, right? I have now omega d. I have also omega. And there is another one which is called omega 0. What are those, right? So omega 0 is the natural angular frequency without even the drag force. Okay, if you remove everything, just like without considering any drag force, etc., and that's actually the natural frequency of the system. And what is omega? Omega, according to that function, okay, omega is defined to be omega 0 squared minus gamma squared over 4 square root of that. That is actually the oscillation frequency, which we actually discussed last lecture, after you add drag force into the gain. Okay? Finally, omega d is how fast you actually drive the system. Okay? So that is actually the definition of these 3 omegas. Okay? So you can see that if I prepare my a solution to be in underdamped situation, then basically you will see that this is actually so-called the steady state solution because the omega d is a constant, so it's going to be there forever, right? And the second term is actually b exponential minus gamma over 2t. It's decaying as a function of time. So if you are patient enough, you wait, then this will be gone, right? Okay? So that is actually how we actually understand this mathematical result. And then, of course, you can actually take a look at this. This is actually just assuming some kind of initial condition and plug in the solution and plot it as a function of time, okay? And you can see that this function looks really weird, looks a bit surprising. What does that mean, right? Looks really strange. But at some point, this superposition of these two functions, because one of the functions actually dies out, disappear, then you will see that, if you wait long enough, then you actually only see a very simple structure, which is oscillation frequency of omega d. And that means at large t, okay, in the beginning, the system will not like it. You drive it, and the system doesn't like it. Like if I go on and shake you, in the beginning, you will not like it, right? Maybe. And if I shake long enough, and you say, oh, come on, okay, fine, I accept that. Okay, so that is actually what is going to happen to the system, okay? So now, I would like to go through a short demonstration, which is actually the air cart, which you see before. There's a mass, and there are two springs in the front and the back of this cart. And of course, as usual, I will turn on the air so that I make the friction smaller, but actually still there are some residual friction, okay? And you will see that this mass is actually oscillating back and forth, okay? And the amplitude can become smaller and smaller as a function of time, okay? Now, in the right-hand side, I have a motor which is actually can drive this. I can actually shorten or increase the length of the right-hand side string. Then actually I actually introduce a driving force by the right-hand side motor. If I turn it on, this is what is going to happen. Okay, so you can see now this motor is actually going back and forth, right? And it has a slightly higher frequency compared to the natural frequency, right? So the frequency of the motor is higher, okay? Then you can see that this cart is actually oscillating, but you can see that sometimes it pauses and sometimes it moves faster, right? It's actually not, you see, so you can see that it's actually moving and it stops a little bit. And because there are all superposition of two different kinds of oscillating functions come into play. You can see that now it got slowed down and it becomes faster and slower and faster. But eventually, if you wait long enough, okay, if we wait long enough, what is going to happen? What is going to happen? If we wait long enough, exactly. So basically, if you wait long enough, as you said, you will actually just oscillate at the frequency of the driving force. You can see that this motion is looks really bizarre, right? Sometimes it stops, and sometimes it actually continue to move. And are you surprised? Probably you are not surprised anymore, right? Because we know math is the language to describe the nature, right? And indeed, it predicts this kind of behavior. That's really pretty cool. Okay? In order to help you to learn a bit how to actually translate a physical situation into mathematics, what I'm going to do is to introduce you another example so that actually we can actually solve it together. So now I would like to drive a pendulum. Okay, so I prepare a pendulum at time equal to 0. Okay, this is a string attached to a ball with mass equal to m, okay? And the length of the string is actually L, and the angle between the vertical direction and the string, the direction of the string is theta, okay? And of course, I can actually give you an initial condition x initial, which is actually measured with respect to the vertical direction, okay? And at time equal to t, okay? This is actually the original vertical direction, the same as this dashed line, okay? And I can actually move this, the top of the string back and forth to some position. And of course, this string is still connected to the ball. And this system is actually driven from the top by Yen-Jie's hand. So Yen-Jie is actually shaking this system from the top, okay? And I do it really nicely. So basically, I define that the displacement d as a function of time is equal to delta sine omega dt, okay? So that is actually what I'm going to do. Okay, and I would like to see what is going to happen to this pendulum, okay? So as usual, the first step, okay, towards solving this problem is to define a coordinate system, right? So what is actually the coordinate system I'm going to use? So now I define pointing upward to be y. I define the vertical, the horizontal direction pointing to the right-hand side of the board to be x, okay? So that's not good enough. I still need the origin, right? So now I also define my origin to be the original position of the ball when this is actually completely which is actually completely at rest before I do the experiment, right? So that is actually the equilibrium position of this system, actually. Okay, then I define here to be 0, 0. Okay, so once I have that defined, I can now express the position of this mass or this ball to be xt and yt. Okay, and see what we are going to get. Of course, as usual, we are going to analyze the forces actually acting on this ball, right? So therefore, as usual, we will draw a force diagram. Okay, so basically, you have the little mass here, and you have actually two forces acting on this little mass or little ball. This is Fg pointing downward. It's a gravitational force, and that is actually equal to minus Ng y. Okay. And there's also a string tension T. Okay. Since we have this definition of theta here, basically I have the T which is actually pointing to the upper left direction of the board. Okay. And of course, don't forget. Actually, there is a third force, which is actually F drag. Okay, F drag is actually equal to minus B x dot in the x direction. Okay. Now, I would like to write down the expression for also the string tension T. The T is actually equal to minus T sine theta in the x direction, right? Because the T is pointing to upper left direction, right? So therefore, the projection to x direction will be minus sine theta. And the plus T cosine theta in the y direction, right? Because the tension is actually pointing upper left, okay? As usual, this is actually pretty complicated to solve. I have this cosine, I have this sine there, right? So what I'm going to do is to assume that this angle theta is very small, okay, as usual. Okay, so I will take small angle approximation. Then basically you have sine theta is roughly to be equal to theta. And that is actually equal to what? Equal to here, basically you can actually calculate what would be the theta, right? Okay, the theta, the sine theta, or theta will be equal to x minus d divided by L, right? And of course, taking a small angle approximation will bring cosine theta to be 1. Okay, then after this approximation, my t will become minus t x minus d divided by L in the x direction plus t in the y direction. Okay, because sine theta is replaced by this approximated value. Cosine theta is actually replaced by 1. Okay, any questions? Yes. Sorry, can you? Oh, this delta? It's a constant. Yeah, I was going too fast. So this is actually a constant of the amplitude. Okay.
And the drag force is only in the x direction?
Yes, it's only in the x direction. So I'm only trying to actually move this point back and forth horizontally. Okay. Okay. So now I have all the components T, Fg, F drag. Okay. And of course, you can see that I already ignore the drag force in the y direction, right, from that formula, okay, because I'm only considering the system to be moving in the x direction, okay. Therefore, I can now collect all the terms in the x direction, okay. Basically, you will have mx double dot. This is equal to minus b x dot, okay, which is actually coming from the drag force, okay, minus t x minus d divided by L. This is actually coming from this term, okay, in the x direction. Let's look at also the y direction, and y double dot will be equal to minus Ng plus t, right? The minus Ng is from the gravitational force, and this t is coming from the y component of the string tension, okay? And of course, since we are taking a very small angle approximation, there will be no vertical motion, right? Yes?
Why did we use the small angle approximation if for sine theta we're going to use x minus d over which represents sine instead of just theta?
Yeah, so actually in this case, they happen to be exactly the same. And what I care is actually the cosine theta. Otherwise, I will have to deal with cosine theta. And also, this y double dot will not be equal to 0, right? Which is what I'm going to assume here. Okay, good question. So the question was, why do I need to take approximation? Because I want to get rid of cosine theta. Okay, so now from this y direction, I can solve t will be equal to Ng, right? Because I assume that there's no y direction motion, then I can conclude that, okay, originally I don't know what is actually the string tension, right? It's denoted by t. Now, from this second equation, I can conclude that t will be equal to Ng, okay, which is the gravitational force. Okay? Then once I have that, I can go back to x direction, okay? Basically, I get n x double dot, this is equal to minus b x dot minus Ng over L x minus d. Everything is working very well. And I just have to really write down the d and the x explicitly. Okay, the d function explicitly. What is d? D is just a reminder, delta sine omega dt, right? Okay, so I will plug that into that equation. And also I will bring all the terms, related to x to the left-hand side, okay, just to match my convention, okay? All right, so now I will be able to get a result, and x double dot plus b x dot plus Ng over L x, and that is actually equal to Ng over L d. Okay, and this is equal to Ng over L delta sine omega dt. Right? So basically, I collect all the terms, put it to the left-hand side, and I write down d explicitly, okay, which is this. Okay, then I can divide everything by m, then I get n x double dot plus b over m x dot plus g over L x. And that would be equal to g over L delta sine omega dt. Now, of course, as usual, I will define this to be gamma. I will define this to be omega 0 squared. I will define this to be f0, and which is equal to omega 0 squared delta. Okay, happen to be equal like that. And then this actually becomes x double dot plus gamma x dot plus omega 0 squared x equal to f0 sine omega dt. Am I going too fast? Okay, everybody is following. So you see that, this equation, I know that. I know this equation, right? Because we have just solved that a few minutes ago, right? Therefore, I know immediately what will be the solution. The solution is here already, right? I have a omega d and the tangent delta, the function form is there. Therefore, I can now write down what will be the a, okay? So a is actually just equal to f0 divided by square root of omega 0 squared minus omega d squared squared plus omega d squared gamma squared. Okay? Okay. So now the question is, what does the result actually mean? I have this function, okay? I have that function, tangent delta. It's solved. It's actually the amplitude of the steady state solution, and also the phase difference between the drag force phase and the steady state oscillation phase, right? So that's actually the amount of lag and the size of the amplitude, right? But through this equation, it's very difficult to understand, right? So what I'm going to do is to take some limit so that actually we can help you to understand what is going on. So suppose I assume that omega d goes to 0, okay? So what does that mean? This is Yen-Jie's hand, and I move it really slowly and see what is going to happen, okay? If I do this, okay, then you will find that a omega d, okay, since omega d goes to 0, right, this is gone, right? Therefore, you will see that omega a will be equal to omega 0 divided by, F0 divided by omega 0 squared, and that is actually equal to G delta over L divided by G over L, and that will give you the delta. So what does that mean? This means that if I move this thing, drive this thing really slowly, then the amplitude of the mass will be equal to how much I actually move, which is delta. Okay, do you get it? In addition to that, okay, tangent delta, since I'm taking the limit of omega d goes to 0. Therefore, tangent delta will be equal to 0, and that means delta will be equal to 0. Any questions? So that means there will be no phase difference. The system have enough time to keep up with my speed. Okay? The second limit, obviously, omega d goes to infinity. Okay, what does that mean? That means I'm going to hold this a string and shake it like crazy, really fast, okay? And see what will happen, okay? So in that case, you will get a omega d, and that will goes to 0 because omega d goes to infinity, right? This will goes to 0. And also tangent delta will goes to infinity. Therefore, delta will goes to pi. So that means they will be out of phase, okay? Any questions so far in these two limits? Okay, so what I'm going to do now is to take a small toy, which I made for my son, who is 1 year old now, because I would like him to learn waves and vibration before he goes to quantum, right? Okay, so I made this toy, and he sort of get it, okay? All right, so you can see now I can demonstrate what is going to happen when omega is approaching to 0, okay? I'm already doing it. Can you see it? No? It's a very exciting experiment. Can you see that? You see that this is the original vertical direction. If I do it really, really slowly, okay, you can see that the amplitude of the ball is actually exactly the same as the displacement I introduced, right? So that's actually kind of obvious, right? Okay, so now let's see what is going to happen if I drive this system like crazy. Okay, not going up and down. That's the maximum speed I can do. Maybe you can do it better, faster, but you can see that nothing happened, right? So the amplitude is close to 0 because what you have been doing is all disappear. I mean, you go canceling each other, right? And it's actually not going to contribute to the motion of this ball. Okay, so now you can see that I can also test what is actually the natural frequency, and what I'm going to do is to oscillate at around the natural frequency to see what is going to happen. Okay, let's see what is going to happen. You can see that the delta is really small, right? Can you see the delta? It's really small, very small, very small. But you can see that the amplitude, the A, is huge. What does that tell us? What does that tell us? Yeah.
We're experiencing resonance.
Yes, we are experiencing resonance. And also, that also tells you that the system is underdamped very much. The Q value is very big. Okay, so if I calculate the amplitude A, okay, now I can calculate the amplitude A at natural frequency, okay? What I'm going to get is, now I can actually plug in omega d equal to omega 0, okay? So if I plug in omega d equal to omega 0, then what is going to happen? So this term will cancel, right? So you have A is equal to F0 divided by omega 0 squared, omega 0 gamma, right? Omega d is now equal to omega 0, okay? And that is going to give you, okay, so F0 is actually omega 0 squared delta divided by omega 0 gamma, okay? And the one omega 0 actually cancel, then basically you will get Q times delta. Okay, what is Q? Just a reminder, it's actually the ratio of omega 0 and the gamma. When the Q is very large, what does that mean? That means it's so close to an idealized situation. The drag force is very small. Okay, you can see that in the example which I have been doing, right? So you can see that, it is really the case, right? So you can see that if my delta is something like 1 centimeter, right? But the amplitude is actually at the order of 1 meter, maybe. What does that mean? That means the Q is actually roughly 100, okay? So you can actually even get the Q out of this experiment, okay? Any questions so far? Okay, that's very good. So now we can go ahead and take a look at the structure of the A and the delta. Okay, as we demonstrated before, we make sense of the 3 different kinds of situation. Omega d goes to 0, omega d goes to infinity, and of course, I would like to know the full structure of those A and delta. Therefore, what I'm going to do is to plot A omega d, okay, as a function of omega d. Okay, so what I'm going to do, what I'm going to get is this will be equal to delta when omega d goes to 0, right? We just demonstrated that, right? And this will increase to a large value and drop down to some to 0 when omega d goes to infinity, okay? And you can see that this is around omega 0, and you are going to get a huge amplitude, okay, at around omega 0, but not quite. The maxima is actually slightly smaller than omega 0. You can actually calculate that as a part of the homework, okay? So that makes sense. Now I can also plot the delta, which is the phase difference, okay? And you can see that this phase difference will be originally 0 when the omega d is very small. And this is actually omega 0. I hope you can see it, okay? And this will be increasing rapidly here and approaching to pi. Okay, so that means when you are shaking this system like crazy, very high frequency, then the system cannot keep up with the speed. Okay, the amplitude will be very small, and also the amplitude will be out of phase completely. Okay, so that's actually do us another demonstration using this little device here. This is actually what you see before, the ball with a Mexican head, okay? And you can see that there's a spring attached to this system, and on the top, what I'm going to do is to use this motor to drive this system up and down, okay, as a drag force, okay? So now what I'm going to do is to come from a very low frequency oscillation. So you can see that the natural frequency is sort of like this, okay? And you can see that, okay, now I'm driving this system really slowly. You can see this is actually going up and down really slowly, okay? And you see that, the amplitude is actually pretty small, right? There's no excitement for the moment, okay? All right, so what I'm going to do is now I increase the speed of the motor and see what will happen. So you can see now it's actually driving it with higher and higher frequency. You see that, something is happening. You can see the amplitude is getting larger and larger. I'm still increasing the frequency, increasing until something suddenly happened, right? Did you see that? It started to oscillate up and down, right? Because right now you can see that, look at the top, okay? The frequency of the motor is now really close to the frequency of the natural frequency of this system, okay? So a resonance behavior will happen, and what you are going to get is that, okay, omega d around omega 0, then you are going to get large time amplitude, okay? So now what I'm going to do is to continue to increase the driving frequency to a very large value. Okay, now it's actually doing this really fast. You can see on the top, very fast. And can I even get it even faster? You see that, indeed, this system is now oscillating at a larger frequency, right? It's trying to keep up with the driving force, but you can see that the amplitude is actually much smaller than what had happened before. So before the class, you may actually think that, okay, drive it really fast, maybe we'll increase the amplitude, but in reality, actually, it will give you a very small amplitude, okay? Another thing which is interesting to know is that you can see that when the driving force is actually at the maxima, okay, and actually this the position of this mass is actually at the minima, right? So they are actually out of phase. Okay. I hope you can see it, right? It's like this. Okay. Okay, so what you can see is that when I understand this system and I try to drive it with the natural frequency, what is going to happen is that I'm exciting this system to a state of resonance, right? So basically, you get some resonance behavior. So I have shown you that this works for driven mechanical oscillator. It also works for the spring mass system, right? And there are many other things which also works, which is around you, right? For example, if you happen to be in my office hour, okay, you will notice that the air condition in my office is actually creating a resonance behavior. You see low frequency sound, something like that. And that is because the pipe is actually happen to have the frequency match with the resonance frequency. Okay, the airflow actually happen to excite the pipe so that actually is actually oscillating up and down at that frequency. So what I did was I tried to turn it down to low and see what happened. But unfortunately, it actually excites another resonance. Okay, I see now not a low frequency sound, but a very high frequency sound. I will post the video actually online. So my life is hard, right? So, but I'm a physicist, so I choose to use the median. then I actually stay between the two resonance, then I don't see, then I don't hear the additional sound which bothers me, okay? Another example is that when I was in Taiwan as an undergrad, I was living outside in an apartment, and with my flatmate, we own a very old washing machine, okay? So in the middle of the night, the washing machine will start to walk around like my flatmate, okay? And we are not scared because the oscillation frequency, actually the rotation, actually happen to match with the frequency of the washing machine. Therefore, when we start to wash our clothes, it starts to walk around in the room. So as a physicist, what we have decided is to make the spin slightly slower. Then as you can see that, or even faster, then actually you can see that when you do that, then you get rid of the resonance behavior. So it's not working around anymore. We can control it, okay? Another thing which is interesting is that the resonance behavior is not only in the physical object which we actually deal with these days also, but after you learn quantum mechanics and the quantum field theory, you'll find that there are resonance also in mass wave function, okay? So basically you can see that this is an example of the Z boson resonance peak. So if you scatter electron and positron, then basically you see that the cross-section have a resonance peak at around 90 GeV, okay? And that is actually another very interesting example of a resonance in particle physics. Finally, the last example which I am going to go through is an example involving a glass. Okay, we have prepared a very high quality glass here. Okay, maybe you have seen this glass before. They are pretty nice, and I usually use it to enjoy my red wines, which you cannot enjoy probably now. So you can see that if this is a glass, and if I put a little water on my hand and I rub it, carefully, I can actually excite one of the resonance frequency. Okay, so you can see that we have always been working on a single particle. Okay, and that will give you one resonance frequency. If I work on two particles, which we will see that in the next lecture, I will get two resonance frequency. And this glass is made of infinite number of particles. Therefore, I will have infinite number of resonance frequency. Okay? When I am rubbing it, I am actually giving input of all kinds of different frequencies. But the glass will be smart enough so that it will pick up the one it likes the most, which is the resonance frequency. So you can see that the sound is actually roughly 683 hertz, okay? And you can actually measure it with your phone, right? Okay? So on the TV commercial, you may have seen that there's a lady singing, and she's singing so loudly such that the glass breaks, right? Can we get a volunteer today to sing in front of us? Oh. Singing. Can you sing it? High frequencies. Very good try, but didn't work, okay? Okay, I guess it's really difficult to perform that in front of so many people unprepared. But fortunately, we are in IT, so we have designed a device which actually can help us to achieve this. Okay, so this device is actually contain amplifier here, and I can now control the frequency of the sound through this scope, and this amplifier will actually amplify the signal and produce a sound wave, and try to actually oscillate this glass. Okay, so we are going to do this experiment. So we will need to change the light setting a bit because the sound is going to be probably too loud. Just for safety, some of you may not survive. So I'm handing out this. Okay. Who is closer? Okay. Maybe you. Yeah. Oh, sorry. I'm so sorry. Well, I don't need that. Okay. So just for safety, I will put this on. And what I'm going to do is also put this glass on, right? Okay, maybe I do this first. Okay, so what I'm going to do now is to start producing sound wave. So through the camera, you should be able to see what is actually shown on the screen. So you can see there's you can see that if this glass is actually moving, the wood inside will also vibrate. Okay, so you can see that clearly we don't have resonance yet. So what I am going to do is to increase the frequency and see what happens. So now it's actually 643. It's actually still below the resonance frequency. Now I have measured the frequency should be 684. So now it's actually 653, 663 hertz, 673 hertz. Can you see the movement? You cannot see the movement still yet. 683. You see now the frequency of the sound is actually matching with one of the natural frequency of the glass. Okay, apparently the glass like it. Okay, and now you can see that it's still vibrating, and the next step which we are going to do is to try to increase the amplitude, increase the volume of the sound, and see what happens. Maybe you want to cover your ear just for safety. Okay, then the glass may break if we are lucky. Okay, so let's see what is going to happen. Very good.
Perfect. That's the quickest one we've had.
Yeah, thank you very much. Thank you, glass. So you can see the power of resonance, right? So if I tune down the frequency slightly more, then it will be where? It will be here, right? Then you will not have enough amplitude to break the glass. And also, as we discussed before, the quality of the glass should be really, really high, such that the resulting amplitude will be very large. Then you can actually break it with external sound wave. And if we go above the resonance frequency, then you will not also move a bit, because because if you go to very large omega d, then amplitude will be pretty small. Okay, let me try to switch back to my presentation. Okay, I think sure. Okay, so this is actually what we have learned today. We have learned the behavior of a damped-driven oscillator. Okay, we have learned the transient behavior. So what is actually transient behavior is actually a mixture of steady-state solution, which is coming from the driving force, and the homogeneous solution. Okay, if you wait long enough, this will decay and disappear. Okay. And we have learned resonance, right? So in RLC circuit, which you actually solve that in your PSAT, in pendulum, which I just showed you, which helped my son to learn wave and vibrations, and air condition, washing machine, glass, particle physics, we can see damped-driven oscillator or resonance almost everywhere. Okay? So I hope that you enjoyed the lecture today. And what we are going to do next time is to put multiple objects together so that you will see the interaction between one particle to the other particle and see how we can actually make sense of this kind of system. Thank you very much. And I will be here if you have additional questions related to the lecture.